Sure.
So our next speaker is Catherine Yan from Texas A&M, who will speak about Gončarov polynomials. Please.
All right. Okay. Thank you, Mel, for giving me this opportunity. My talk is based on joint work with two of my graduate students, Ayo Adeniran and Lauren Snyder. The plan for the talk is first, I'll introduce the classical definition of parking functions, which is a combinatorial object, and Gankarov polynomials, which is coming from interpolation theory. I'll say what they are and what's the connection between them. Then I'll introduce the multivariate interpolation problem, and that leads to a multivariate version of the Gankarov polynomial. We find a combinatorial interpretation of those polynomials in terms of integer sequences, and which led to a higher dimensional generalization of parking function. Then at the last part, I have to use the algebraic formula for the interpolation polynomials to give some enumeration result for the integer sequences. So first part, classical parking function, this actually well-known object having many equivalent definitions. I will adapt the one which is kind of go along with the interpolation polynomial. So here's definition. We're interested in integer sequences of length n, and given us a sequence, the numbers can be messed up. So the first thing, you want to sort it from small to large, and just write them as a sub 0, a parenthesis 0, a parenthesis 1, etc., which the ith term is called the ith order statistic. Just here to go along with my index in polynomial, my minimum index is 0 instead of 1, which is typically seen in other paper. So for such a sequence, we say it is a parking function if and only if the ith order statistic satisfies inequality, the number is an integer lying between 0 and is strictly less than I plus 1, so just up to the number I. So I gave some example, which are parking functions, to say why they are parking function. Maybe just say one example here. So let's 32004. What you want to check is first rearrange them from small to large, which you got a 0, 0, 2, 3, 4. Then you want to compare them with the kind of the standard numbers, 1, 2, 3, 4, 5. And term-wise, you say, okay, the bottom one is always larger than the top one. So here, good, this is a parking function. That's all you check. On the other hand, if you have 1, 1, 2, 3, 5 to start with, then it's no longer be less than 1, 2, 3, 4, 5. So that's not a parking function. So I hope the definition is clear. Among older parking functions, there's a special family, the monotone cases, which whenever I say monotone in this example is always monotonely increasing. Oh, actually, it's just weakly increasing, or you say non-decreasing. So we want to define those parking functions which the terms are already sorted from small to large. The traditional reason is called increasing parking functions. And those parking functions of size n are counted by Catalan number, which I'm happy that Noah mentioned the list in the previous talk. So this, I'm using the nth term. So this is 1 over n plus 1 to n chooses n. And to see why the increasing parking function corresponds to me counted by Catalan number, I want to give you an easy illumination where I think well-known representation of Catalan number is the lattice passes controlled by diagonal. So it's kind of lattice pass from 0, 0 to n, and lying just below or on this diagonal. So actually for any increasing part sequence, which if it is a parking function, you can realize it as a lattice path. Well, as follows. Here I have the example 0, 0, 2, 3, 4 from the previous page. So we can think in here as a lattice path whose horizontal steps are at the height 0, 0. So here's height 0, horizontal step, height 0. Then you want a height 2, height 3, height 4. Then you just connect them by the vertical edges, these horizontal steps. Now you end up in a lattice path, which is staying sub-diagonal. And you can easily check the condition for the parking function. The inequality I mentioned in the previous page is exactly saying it's under diagonal. not exceeding the diagonal. So far we kind of introduced these two object parking function and its monotone analog. This kind of representing two of the most basic combinatorial structures, which is count by Catalan number. Sometimes I just prefer to mention this as an unordered structure. It's kind of most like because either it's unordered or you have a specified order, so you don't have freedom to shuffle the terms. As I mentioned, the typical example is the sub-diagonal lattice path I just drew, but it's also including valid sequences, plane trees, binary trees, triangulations for, I think, plane polygon, non-crossing or non-nesting matching, so partitions, a lot of pattern avoiding permutation problems, and some standard Young tableau. And as Noah mentioned in the previous talk, in the dope matrices of two rows. On the other hand, there are another family of structure count by Cayley's formula, n+1 to the power n-1. The typical example is labeled tree on n+1 vertices with this family, also including parking functions of length n. This is kind of a lot of situations. The structure is obtained by, you have some Catalan structure in the background and allowing certain labeling or ordering, then you got this something counted by Cayley's formula. Examples also including labeled deck paths, certain kind of a nice hashing function in the random hashing appear in the interval orders, region of hyperplane arrangement, and the chains of lattice of non-crossing partitions, and so on. I just list some. So it appears in a lot of algebraic and representation problems. So here is the combinatorial structure. Next, let's go to the interpolation polynomial, a special polynomial called Gankarov. So it is arising from a particular interpolation problem where people in numerical analysis or approximation theory has been studied for a long time. It's called the Gankarov interpolation. So the problem is the following. I think in the, I just assume it's a real plane, real or complex, doesn't matter. You just given n+1 numbers. This is kind of the points. And in your mind, you have n+1 values. So what you want is to find a polynomial of degree up to n, so that when you take the ith derivative of this polynomial, then evaluate at the ith point, then you got the ith value you want. So here is the problem. And it turns out that such an interpolation problem always have a unique solution. To describe the solution, we can thinking about a basis case, so which is obtained by lighting the value you want to be everywhere 0, except the largest number. The large number Bn is n factorial, while the reason for n factorial but not 1 is because we want the polynomial to be monic. So it's actually a scaling factor. Then we will have a unique solution to the interpolation problem, and that solution is called the nth Gankarov polynomial. We'll write as Gn. Is depending on x, and of course, depending on the parameters a0 up to an-1. Well, it wouldn't depend on the last number, last point an. So here is some formula for what the polynomial looks like. The first two are still fine, but later you can see the formula can get quite involved. And that's not a surprise because we have like n parameters anyway. There are two very nice cases. First, when the points you want is the same point, we just get the standard power. And in the other hand, if the interpolation point we want is linear, means it's a arithmetic progression, then what we have is a nice product. This actually is something like a shift of the Abel polynomial. This function, although the exact formula is not that easy to write down, nevertheless, this polynomial sequence has many equivalent definitions in terms of a differential equation or recurrence or generating function, and satisfies some nice algebraic equations. So this allows us to compute those things or get properties. We can get a lot of nice properties. So what's the relation between the two things I talked about? It turns out the Gankarov polynomial offers you the right algebraic tool to study parking function. And it's kind of the secret is revealed in this theorem, which is Joseph Kohn and I found many years ago. So the theorem says you give a vector u, where you can think it's an integer sequence of non-decreasing integers. Then this Gankarov polynomial Gn on some special node, actually by the invariant property of Gn, you can think that's the constant coefficients of this Gankarov polynomial that actually give you the counting of something called U parking functions. Well, we know what's parking function. What's U parking function? Just one step further. So a U parking function is a sequence of n integers where when you rearrange them from small to large, the ith order statistic is lying between 0 and strictly less than ui. As we mentioned from beginning, if this u is 1, 2, 3, or n, that's the classical parking function. If you take some arbitrary vector just increasing, I mean, it can be type weakly increasing, then you got a vector form of the parking function. So let's solve the parking function. And also we kind of looking for the other family we're interested in is the increasing parking function. The polynomial I just defined doesn't tell you how to count the increasing one, but that's actually not too much different. So all you have to do is in the interpolation problem, replace the derivative by the backward difference operator. So which is operator delta, I write as big delta, which applied down a polynomial is px minus p on x minus 1. So, and you consider the same interpolation problem, and you got a new family of polynomial, and this is called the difference Gankarov polynomial. So it turns out that one, up to a scaling factor n factorial, give you the same kind of correspondence to the sequence of increasing parking functions. Oh, actually, we can say that's increasing integer sequences with a fixed upper bound. So you can just don't ignore the parking function term. And the line I put on the bottom here is just means algebraically, Gankarov polynomial or the difference analog, they are very similar. Actually, basically, they share the same property, but with a little small corresponding change. So this is the classical result. Then our goal is to kind of extend the listing, consider all the setting into multivariate case. So first, we will introduce to you what is the multivariate Gankarov interpolation. Well, it turned out to be a very nice problem. So first, you fix the index set, capital S, Mn, which is just all the pairs ij, where I is from 0 to m and j is from 0 to n. And we're looking at all the polynomials of the degree up to Mn. So the problem is as follows. Based on the index set, for each index, you find a node is a point you want. So you have basically n plus 1 times n plus 1 many points. Also, you have the same number of values. And what we want is looking for a polynomial of degree up to this Mn, so that for this polynomial, the standard one is take partial derivative to x, I times, then to y, j times, then evaluate at zij. So this epsilon here means evaluation. After this evaluation, you hope to get the value bij. The difference analog is replacing the partial derivative by the difference operator, backward difference operator, first to x, I times, then to y, j times. Then same thing, evaluate at the point zij, and you want to get a desired prefixed value. It's not hard to see that it's basically just a linear algebra, that such interpolation problems in a higher dimension, well, I have to say, in my talk, a higher dimension actually can be k-dimensional, but just to make things simple, I always only present when the dimension is 2. All the results can be extended to higher dimensions. So back to the definition. So what we have for such interpolation problem is always has a unique solution. And the same as before, we can describe the solution by looking at a kind of a basis of the solution space. And the basis is obtained by, for those value bij you want, you put them everywhere 0 except the one, the biggest, the one corresponding to maximum index to be non-zero. For a scaling purpose, you call this n factorial times n factorial to guarantee that the polynomial obtained is have the leading coefficient 1. So for the classical partial derivative, you got two-dimensional Gankarov polynomial, gnxy, and for the, if we use the difference operator, that's we call it twiddle gmn, the difference Gankarov polynomials. Exact formulas for those polynomials are pretty messy. So I kind of, it's a little bit hard to compute, especially when the mn goes a bit larger in the general case. But I just want to present for you a special case, namely the linear case, where the nodes have coded xij, yij. Both of them are linear functions of the coordinate I and j. This is the case. You can say first we can compute them. You can have an explicit formula either in the standard case or in the difference analog. The Gankarov polynomial is two variable Gankarov polynomial. Kind of each of them is a product formula of pretty nice linear factors. And the second, I think this is the first non-trivial case, meaning that unless this the coefficients are special, otherwise these polynomials cannot be written as a product of one polynomial in x times another one in y. So this is kind of not separable, but it is still controllable. And the linear case is important because if you recall in the one variable case, the classical case, that's where you get a Cartan number and Abel polynomials. So here we have this kind of little bit complicated polynomials. So how to understand this combinatorially? What's the relation with the combinatorials? Or can you find some relation with the integer sequences? Well, it's kind of took us some time, but we did find one. So it's a little bit kind of need a little bit definition. So let me explain to you what happens. So first, you think we will have a grid on the integer point from 0, 0 to mn. So kind of you have such a grid. And you think this is a graph. And on the grid, every edge will have a weight. Typically, we'll say edge, horizontal edge have the weight uij, and any vertical edge have the weight. The weight is vij, where ij is the starting point of that edge. Okay, so here is have a weighted grid. Then for a pair of integer sequences, the first sequence have length m and the second one has length n. We'll assume they're already arranged from small to large. We'll say, here's the crucial word. This pair of integers sequences is bounded by some lattice path p with respect to the weight. If and only if something like this happen. So what we have is, suppose you have a lattice path in that grid, and you want to label the horizontal edges by the A sequence and the vertical edges by B. And you want on every edge, the label is less than the weight. Let me show you a more concrete picture. So here is the example. I have a grid of size 3 by 4, and along the line, I wrote down all the weight. This one is given by the linear case where the horizontal one has the weight is fixed the height of that horizontal edge, and for the vertical, it's basically the x coordinates of that edge. So under my pair of integers, the first one is 2, 2, 3, and the second one is 0, 0, 1, 3. In this picture, so let's take a lattice path, maybe this one. This is from origin to the right corner. And on this lattice path, I will write down my label. On each horizontal edges will be labeled by the sequence A. So the two, oops. So here is 2, here's a 2, here's a 3. The horizontal edges have this label, and the vertical edges one by one by the second sequence. So 0, 0, 1, 3. That's the label for the vertical edge. Then I compare for every edge. I want to say whether the label is less than the weight. And in this picture, I do have this true. So in this case, I'll say this two sequence, the pair of sequence is bounded by this lattice path according to the weight. And of course, maybe the lattice path may not be unique. In this example, I think actually this is another. I think here is another lattice path. We'll do the same trick. That we really don't care which is the lattice path. All we care is whether there is a lattice path do the job or not. So here is the combinatorial kind of description of whether the integer sequences are bounded by some lattice path in the grid. Okay, so here we can relate our polynomial to the integer sequence. So giving some x, y, we assume they are positive, they are large positive integers, and giving the set of nodes z, we can define some weight. Basically, it's the difference between the x and the coordinate of those points. Then when we try to look at the pair of monotone sequences, which are bounded by some lattice paths with respect to the weight, it's just as what we described in the previous page. Then this number is actually captured by a rescaling of the difference Gankarov polynomial. On the other hand, if we just starting with the structure, we just have the double sequence, but which is monotone, and we can freely just permute the entries. And whenever we get a different sequence, which is counted once, so we're looking at all possible ways to mess up those entries. Then we got those double sequences whose order statistics are bounded by some lattice path. Then that number is enumerated by the standard Gankarov polynomial in two variables. So this result definition here, we can think this gives us a definition of increasing parking functions with respect to weight u. And here, when you allow to swirly shuffle permute the entries, we got a definition of parking function with respect to the weight mu in 2 dimensions. So let me mention how the result we have in the obtained from the interpolation polynomial help us counting those parking functions or increasing parking functions. Again, we will be interested in the case, which is, we call it a fun case, because the weight is given by the linear functions of coordinate I and j. So using the linear form we obtained in several pages before, we can get computing that the number of monotone u parking function and the number of just arbitrary ordered u parking function are given by these two formulas. Something interesting to see is the general parking function, we have the powers here, and for the increasing one, we have here is the upper rising factorial, which not surprisingly, you can see that's what you expect to see, because that will kind of relate to some binomial coefficient kind of thing. Let's look at the interesting, and actually it's the easiest case in those polynomial, in those form where the matrix, the coefficient matrix is 0, 1, 1, 0, and the ST term is 1, 1. I would say this is the easiest one. I think you may be wondering why I don't take a diagonal matrix or identity matrix. The reason is that's not interesting, because that will give you just the two variable Gankarov polynomial is the product of two one-dimensional things, separable, so that's not interesting. This is the easiest case, but where you cannot separate x and y. In this case, what we have is the number of monotones, so the increase in u parking function is given by this kind of product of two binomial coefficients over 1 plus n plus n. This happened to be something called a Narayana number. In combinatorics, this appears often. It's well known as a refinement of the Catalan number. And on the other hand, over all general all parking function, the number is this nice power. We are happy to see that actually these two results agree with the existing result for a notion of PQ parking functions introduced by Corey and Polahan. And they introduced a kind of a very special parking scheme and obtained some integer sequences, which turn out to be counted by this number. But their real motivation is not that parking scheme, is they're considering is the center pile models on a complete bipartite graph with additional nodes. And from there, looking at the critical configuration of the center pile model, and this is the result they obtained. So to finish, I'd like to introduce an interesting equal ratio result. Notice my top, the classical case, the top equation, at least here, thinking of the classical parking function where every term is lying between 0 to n. So you can think all the terms, sequence of integers of length n, where all the terms are coming from 0 to n. So this is the all the sequences we're looking at. The number of such sequences is n plus 1 to the power n, and the classical parking functions are all there. So the equation here, what it's talking about is saying over such sequences, the portion which are parking functions is the same of the ratio of increasing parking functions, which are the constant number, over all the increasing sequences in that word. So this is kind of something happened in the classical case. Well, with the help of this linear form we obtained, actually we can say this for any fine weight matrix U, we actually can have the same thing happen. So if you have a proper defined total space, I call this X, which including all the U parking function, then in that word, the portion of U parking function in those sequences is the same as the portion of increasing parking functions over all the increasing sequences in that word. And that word is actually very simple. That's just the double sequences where the first sequence of length m and all the terms lying between just some fixed interval, and the second sequence of length n, all the term kind of coming from another fixed domain. And what the domain really is, we will see this bound is actually the maximum weight allowed by that affine U. And all these results actually true in higher dimensionals. So I guess I'll just finish my talk here, and thank you for listening.
Thank you very much. Any questions for Catherine?
Yeah, hi, Catherine. Yeah. Just a quick question. So you have this two-dimensional path earlier.
Two-dimensional path?
Yeah. So
okay.
When you can talk about two variable, right? So
here?
Right.
Okay.
So can you regard this as a kind of composition of one-dimensional one by some kind of shuffle product? This looks like a, one interpretation of shuffle product. Horizontal is one, vertical is one, right?
I don't think so. The reason is I'm counting the sequences here, and the lattice path they can define is not unique. So this actually, you take the summation, you cannot just the summing over. So for each path, how many sequences, I mean, they can correspond to the add together, because that's where we have overlap.
Yeah, but it's shuffle product, you can have multiple terms, right?
But so it's just the one every how do I say this? Maybe I have to really study what's the exact shuffle product you mentioned, but just in the proof actually this one cannot be done by go over the path which kind of define the shuffle how the things shuffled in.
Okay, well just curious, yeah, because it looks kind of similar. And you don't consider this diagonal one, right? So only one step right or up, you don't have diagonal.
Right. The grid is only containing horizontal and the vertical steps. There's no horizontal steps.
Okay, so no diagonal path. Yeah. Okay.
Yeah, that's correct. Yes.
Okay. Thank you.
Thanks.
Thank you again, Catherine.
Thank you, Mel.